Hello, welcome to the next lecture. This lecture, we're going to look at kinematics in one dimension. Looking at the learning outcomes, we're going to try to concentrate on vector diagrams, mostly by understanding what vectors are. For everything else, the outline will go that we're going to explore the concepts attached to kinematics, which is a way of referring to motion. We'll introduce the kinematic equations and the conventions for using them. We'll begin to apply concepts to problem solving, and we'll consider a specific class of problems known as free-fall problems. In order to examine the behavior and interaction of different objects, one of the first things we need to understand is whether the object is moving. And to do that, we need to know its position. Before we can understand those quantities, we have to refer to kinematics. Well, objects that we usually interact with will exist and move in 3 dimensions, which means we'll have an X, a Y, and a Z coordinate. We're going to limit this lecture to focusing on 1 dimension. So here we just use 1 dimension. Now, every time you work through a problem and you provide me with a solution, you should also have a sketch, and in that sketch you need to include a coordinate axis like I've drawn. And this identifies the positive direction. So with 1 dimension, it's just one line with this symbol that says positive. And when you have multiple components of motion, then we need to list all of the ones that we will apply. And in this course, we'll look at 1, 2, and some 3D problems. Our most basic investigation of kinematics is the necessity of needing to know where an object is. There are 2 concepts that deal with the location of an object. The first is position, and we represent position with an X and a little arrow over top. This is a vector quantity, which means it has a magnitude, a size, and an amount to it, and a direction. And both of those components of position need to be reported. When we measure position, we always measure it to an origin. So if we look at the number line below, we can mark on a 0 point, which we would call an origin, and we can determine that any displacement to the right would be a positive displacement, and any displacement to the left would be a negative displacement. So we can even label in amounts here. Looking at this measuring tool, I would say we could label the +1, +2, and +3 positions, as well as the -1, -2, and -3 positions. Let's start to look at an example here. Let's consider the position of this orange and this purple dot. So the position of the orange dot. So here we'll use the symbol X with an arrow over top and the subscript of just an orange dot in this case to represent it. So the position of here is 2 to the right of the origin, which we can write as such, or we can write with a +2. The purple dot, which we'll represent with X and the subscript of a purple dot, is 1 left of the origin. And with the convention we established here, left being negative, we could write this position as -1. Now that we know how to represent the position of an object, we consider whether or not the position of that object has changed. This quantity is displacement. So displacement, represented with a little triangle and an X with an arrow over top, is the change in position. We can consider a change in position if we have 2 positions identified. So let's consider the displacement moving from the orange dot to the purple dot. And notice that's the way we represent our subscripts here, with the orange dot first and the purple dot second. And if we do this, we can simply count the number of positions. So we start at the orange dot and we move all the way to the purple dot, which is 1, 2, and 3. So our displacement, or our change in position, is 3 to the left, which can also be said as 3 in the negative direction, which is based on our coordinate system we set up. We won't identify change in positions by drawing them every time. We need to be able to calculate this value. So the change in calculation from displacement is an important tool, and we're going to use it with many of the quantities in kinematics. Whenever we have 2 or more points, we can consider a change in between those 2 points of interest. That little triangle symbol is actually the Greek letter delta, and that represents our change in. That calculation will always be calculated as whatever the final value is, subtract the initial value. One of the common ways to represent a displacement is the delta x formula, and that would be equal to x final subtract x initial. The subscripts can change, and so too can the symbols. So some of our calculations will be done in the x direction, but some of them could be done in the y direction. So we could calculate a change in y position. And here that would be delta y, and our subs should be from 1 to 2, and then we would do y2 subtract y1. Another convention is that we could be moving in the z direction, and we could have subscripts that say our z position with no subscript, and subtract from that our z origin, which sometimes is 0, sometimes is some other value. And as I mentioned before, our change in calculation will be completed with many of the quantities. So we can also consider a change in time. So whatever our second point in time is, subtract from that our first point in time. We can calculate a change in over any time interval as well. And we'll look at what that means in a minute. I want you to be comfortable with the fact that the change in can be applied to everything, even though the formula sheet that you're going to get will only contain the delta x version. If you want to work in y, z, r, or any other components, you just change out the x component for the component you are working with. Not all changes in location are equal. To compare changes in location, one of the ways we consider this is we look at the amount of time it took for that change in position. We do this so that we can attribute a numerical measure for how quickly location is changing. And we introduce the following quantities. The first thing we talk about is speed. Now, speed is a scalar quantity, and we're going to represent that with a v. Scalar means that this has magnitude but no direction. So we just care about the amount of speed. Now, speed in your everyday language is often just looked at as distance over time. In physics, distance traveled and displacement are two different things, so we have to be careful. The way you typically use speed as distance over time is more correctly referred to as average speed. Our main focus when we talk about change in position over time is velocity. Velocity is a vector quantity, so it is the v with an arrow over top. Because it's a vector, it has a magnitude and a direction. As I said, this is almost always what we are considering when we consider a change in position over change in time. And that phrasing is the definition of velocity. The equation we use is that v will be equal to our displacement, or change in position, over our change in time, so delta t. And that's the version of your equation that you'll get on your formula sheet. When we say speed in physics, what we really mean is an instantaneous magnitude of velocity. When objects are in motion, often they move at different rates in the middle of the same journey. To deal with this, we have to be aware that there's two different considerations of motion. We can think of an average velocity, and this would consider the velocity over an entire time frame, and it's estimated to be constant in that time frame. So well, as we think of the total change in position over time, which is just expanding out that delta x formula, we often have no information about how the object is moving during that time interval. It could be speeding up, slowing down, but we don't have data recorded for that. So when we complete this calculation, we're really getting an average that it would have taken to travel that same amount of distance over that given time. And the calculation automatically assumes that that has a constant velocity at the average value. We need to be careful. So we've called this our average velocity, and we'll see that there are actually several different applications and several different uses of that word average velocity. The other way we think about a velocity is an instantaneous velocity. So this considers the velocity during an almost infinitesimally small time frame. And this is trying to pin down velocity to being actually constant. Now, the magnitude of an instantaneous velocity is what your speedometer in your car is trying to display to you. But in reality, it's very difficult to calculate this value. So what's happening is we're actually predicting it by considering intervals of time slightly before and slightly after our current instant of time. Why is it so difficult to calculate? Well, think, if we're trying to calculate v as delta x over delta t, if we go to an extremely small interval of time, so delta t goes to 0, then our calculation becomes undefined. It makes it very nearly impossible to calculate an actual instantaneous speed. So often what we're doing is assuming that an average velocity calculated around a time of interest will provide our instantaneous velocity for any given time. When we have problems where velocity is not constant, then we have something called acceleration. Acceleration is defined as the change in velocity over change in time. So we have the equation a with an arrow over top is equal to delta v with an arrow over delta t. The arrows signify that acceleration is also a vector quantity, which means it has a magnitude and a direction. The sign associated with our acceleration will be our inference of direction. That means whether or not our velocity is changing in the positive direction or changing in the negative direction. Let's look at the dimensions, the units of acceleration. So it's calculated using delta v over delta t, which means it's giving us units of meters per second divided by seconds again. When we simplify that, it means we have meters per second squared. What this is trying to tell us is that every second, my velocity changes by a given meters per second. We read this off as meters per second squared. It's effectively meters per second, but meters per second squared is the preferred way of reading it. One of the interesting things about acceleration being in a vector quantity is that a change in direction, even with no change in magnitude of the velocity, would still count as an acceleration. So objects going around circles at a constant magnitude of velocity are accelerating towards the center of the circle all the time. We're going to, sorry for the pun, circle back to that in a couple of units. I need to alert you to a very common misconception. A negative acceleration may not mean that an object is slowing down. I want you to be very careful about using the word deceleration. We're always going to properly talk about a change in velocity as an acceleration and then assign it a positive or negative value. So let's consider all the combinations we can have with acceleration. Here we look at the tuples of velocity and acceleration. And we're just going to look at the signs on them. If we create a grid of 2 by 2 that lists velocity across the horizontal and acceleration on the vertical, and we start with the situation where we have a positive velocity and a positive acceleration. This would mean that the object is moving in the positive direction and getting faster in that positive direction. What happens in the region below it where we have a positive velocity but a negative acceleration? So the object is still moving in the positive direction, but it's getting slower as it progresses. It's losing velocity. Let's consider a negative velocity and a negative acceleration. Well, this is just the reverse of our first situation. Here, our object is going to be moving in the negative direction and it's getting faster in that direction. And the final combination is the negative velocity with positive acceleration. And this would describe an object moving in the negative direction, but it's getting slower as it goes in that negative direction. Anytime we have a mismatch of the signs between velocity and acceleration, if we continue that acceleration long enough, we will change the direction of motion and begin to move faster in the direction of acceleration. With each of our concepts of motion, we've introduced an equation to make that quantity calculable. So when we talked about displacement, we said that our delta x will be equal to xf minus xi, and we talked about how that can show up in many different forms. When we introduced velocity, we had v is equal to delta x over delta t. Acceleration is defined as the delta v over delta t. And another way of looking at average velocity over an interval where we don't have constant velocity is if we know the initial velocity and the final velocity and add them together and divide by 2, literally averaging them, we can calculate an average velocity over a time interval. Something we didn't refer to but still does exist is that we can have a change in acceleration, so a delta A, and that's just considering an acceleration final minus an acceleration initial. These situations do happen, but they represent problems that are more difficult than the ones we want to work with in the course. So it's very important to note that the following equations that we look at require constant acceleration. So our change in acceleration must be 0. That means we can have an acceleration of 5, as that would be constant, or we can have an acceleration of 0, meaning that we would have constant velocity. These equations are all based on the definition of the term. Often when we do experiments, we don't have direct access to be able to measure the quantity we're interested in. So what we do is we measure some other quantity and then make a calculation about the thing we want to look at. The way we come across those calculations is we start to combine our equations of motion. Well, I don't expect you to be able to derive these equations. I do think it's valuable for you to review your textbook and see how each of these were developed by combining your equations. There are problems where you will have to combine several equations of motion. For now, let's go through what each of these represent. As we go, I'm going to add vector arrows because really these are all vector equations, even though their scalar version is listed here. The equation on the far left lets us know that given an initial position and an average velocity during a time that an object spends traveling, we can calculate a final position. The second equation says that if we know an initial velocity and an acceleration during an interval of time, we can calculate the total displacement that an object would experience. The next equation over is kind of difficult to see conceptually, but if we look at it, this is our first equation that doesn't depend on time. So in some of our investigations, we won't have a measure of time during an interaction, but if we can calculate the initial velocity, we can connect that to our final velocity if we know the acceleration and the displacement. And the final equation on our list is really just a simple rearrangement of our acceleration definition. And it says that if we want to know the final velocity of an object when we know the initial velocity and the amount of acceleration it undergoes, we can calculate how fast it will be going after an interval of time. Kinematic problems come in many different forms and have very complex setups. To solve these problems, we make several assumptions, and assumptions can be very helpful because they can provide us additional given information or even an additional equation that we could apply. Sometimes our assumptions even cancel out variables in an equation and make it easier to solve. Some of the ways we do this is that we acknowledge we can choose our reference points. And sometimes this will simplify the problem. So often when we look at a sketch of a coordinate grid, there's a fixed origin, but we can move that origin and take it with reference to one of our points of interest, effectively canceling it out. Whenever we take an initial value as 0, this would be moving the origin to that position, it simplifies the change in calculations. So if we consider our initial time as time 0, then delta t would be time final minus time initial. But subtracting a 0 means that our delta t is just equal to our position in time final. Our equations of motion require that we make the assumption of a constant acceleration. So we can break problems up into multiple time intervals where there is a constant acceleration so that our velocity changes consistently each time. That term, constant acceleration, is important. I want you to make sure you understand what that means. So constant acceleration means that acceleration does not change. It doesn't tell us about our velocity. So constant velocity does tell us about our acceleration though. So constant velocity will mean zero acceleration, but constant acceleration could mean a constant acceleration of 0, or it could mean a constant acceleration of 5, in which case the velocity is changing. An excellent example of the benefits of making assumptions about problems so that we can simplify those problems are seen when we consider the class of problems that involve objects in what's called free fall. When we have objects in free fall, we have several assumptions. The first assumption is that the object is falling near Earth. This means that we can apply our first fundamental constant that's been discovered. When an object is falling near Earth, that means we can assume an acceleration that is equal to this value g with an arrow on top, which is defined as the acceleration due to gravity. And that value for all objects in the absence of air resistance is equal to 9.80 meters per second squared down. A little bit of an aside here, that value actually changes based on some pretty complex calculations for how far away from the center of Earth your center of mass is, but it's generally accepted to take this value of 9.80 in our region of the world. If we were at a higher elevation, it would be a little bit less, and if we were closer to sea level, it would be a little bit more. The second assumption we make is that our motion of free fall objects is ballistic. Ballistic means that the motion is determined entirely by the initial velocity. So after an object is launched, there are no other velocity inputs. So our object doesn't have engines, and it doesn't have wings, and it doesn't have a rocket. We also simplify free fall problems by ignoring air resistance for now. This means that once an object is in flight, gravity is the only effect on it until impact. These two assumptions combined mean that there are other known aspects of free fall problems. If an object has an initial vertical velocity, then when that object reaches max height, it will have a velocity of 0. How do we know this? Well, let's just consider the object in free fall. As it's moving up, the acceleration is constant and it's back down, which means that at any point in time, if it still had positive vertical velocity, the object's about to move higher. And if the object had negative vertical velocity, that means the moment before it was at a higher position. So the only time the object can be at its max height is the instantaneous point in time when its velocity is 0 before it begins to accelerate back towards Earth again. Because the acceleration is always constant, the other thing we know is that if we consider both a trip up and down for an object in free fall, the vertical velocity will have the same magnitude at every height on both the way up and way down. So if I throw a ball up with a velocity of 5 meters per second, when it hits max height and comes back down, it will be traveling 5 meters per second when it gets back to the height I threw it from. We can use these assumptions to add given information to problems that we have determined are free fall problems. Now, some kinematic problems are as simple as applying one equation. But when we're faced with a kinematic problem that requires more than one concept, we will need to work through that GRASS method of communication outlined in our previous lecture. And often the most difficult part of this problem is determining whether or not you need multiple equations and which of the equations or concepts apply. When we're solving problems, we need to keep a mathematical fact in mind. When looking at our equations on our formula sheet, any kinematic equation can be rearranged to isolate any one of the single variables, and we just have to apply our algebra skills. And the other mathematical fact is that for every one equation with only one unknown variable, you can evaluate that to get a value for that unknown variable. So when you're trying to select which equation to use from our kinematic equations, you're considering the information you have and the information you want, and you're trying to find one of the kinematic equations or a combination of kinematic equations where the only unknown value is the one you're after. When looking at an equation, for each unknown, we need one equation. So if you look at an equation and it has two unknowns in it, you'll have to look for a second equation to substitute into it to get rid of that second unknown. That fact means that we can actually combine multiple equations, and that follows some of the steps you saw in your textbook for deriving our kinematic equations. So let's look at a few examples. Our first motion problem. A vehicle applying its brakes is known to have a magnitude of acceleration of 6.25 meters per second squared. The typical driver has a reaction time of 0.600 seconds. If the vehicle is traveling 22.2 meters per second, when the driver spots an obstacle 61.0 meters in the road ahead, will the driver be able to stop the vehicle before colliding with the object? So let's consider all of the information we have. So let's look at our given step. We have the values 6.25 meters per second squared. We have a value of 0.600 seconds, of 22.2 meters per second, and of 61.0 meters. In the given stage, it often helps to draw a sketch to give yourself an idea of what's going on and where all the values fit in. One of the other problem-solving strategies that you can apply here is that understand you will always have to read a problem multiple times. Once to get an idea of what's going on, and other times to extract the information you want to use. So let's consider what's happening here. We have a vehicle that's driving along, and this is before anything happens. And then we have our first point of interest. And after that point of interest, the driver begins to react. So this is where our reaction time carries in. After that reaction time, the vehicle is now braking. And at some point in time, that vehicle is going to come to a full stop. So we've drawn some lines on here. So the final one means we've come to a full stop. The middle one is when the driver starts to apply the brakes. And the first one was when the driver spots the object and starts the whole event. Let's refer to these three lines as specific instances in time. So we're going to start from when the driver spots the object. We're going to say that's T0, which is our initial time frame, our reference point. And from there, we're going to call the middle line time 1. And we've already talked about that's the point in time when the driver finally reacts to the object. And then the point in time where the driver comes to a full stop, we're going to call that T2. Identifying points in time helps us start to identify where our values fit in and generate our equations that we're going to use. So with our points in time referenced, we can look at that first given value we have. And it's meters per second squared, which tells us it's an acceleration. And because the driver is braking, we're going to take positive to be to the right, which puts our acceleration as negative. And this acceleration occurs from time interval 1 to time interval 2, so we give it that subscript. The next value down is that 0.600 seconds. And this is our change in time from time 0 to time 1. So as we said earlier, T0 is equal to 0, T1 is equal to 0.600 seconds. And we don't actually know at what time the driver comes to a full stop. So T2 is unknown. The 22.2 meters per second. This is our initial velocity. So this is the speed that the driver is traveling at before they apply the brakes. So that occurs before the problem. That also occurs from the time interval of T0 to T1. And then after that, we'll start to slow down because we're braking. Our last value here, 61.0 meters. So this is the distance away that the object is from the point in time that we see it, but we're not actually going to use it in the calculation. We're going to use it in the interpretation of our results. And this happens sometimes where we have values given to us that we can't use in a calculation right away. One of the things you should notice here is that we've split the problem up into two different sections where acceleration is constant. So in the reacting section, acceleration is 0, and in the braking section, the acceleration is negative 6.25 meters per second squared. So those two values are different from each other, so we keep them separate as two different time intervals. We also said that time interval 2 comes when the vehicle comes to a full stop. So that gives us a little more information. That tells us that velocity at time 2 needs to be 0, wherever that position is. I think it's time to start moving on to our tools here. Now, what we just said about time 2 is important, wherever that position is. So that position is at the end of our total displacement, and that will be the displacement covered during our reacting phase, which is from T0 to T1, and the displacement covered during our braking phase, which is from T1 to T2. And we can represent that with a simple total displacement equation, adding the two together. Some of the other tools we're going to need to use here is that let's think about our definition of velocity. So if we know a velocity and a time, we can rearrange for a displacement, which means that under constant velocity, we can use that definition and define delta x01, the distance covered while we're reacting, as being calculated by taking the velocity and multiplying by the time. And we have both the velocity and time in that interval. The next interval we have is a little more tough. We know the velocity right at the start because the object will be traveling 22.2 meters per second. And we know the acceleration, and we know the final velocity, and we're after the delta x. And again, we don't actually know that time too, so we don't know our change in time. So this should signify to us to look for that v2 squared minus v1 squared plus 2 times acceleration times delta x. Anytime we're talking about velocity, acceleration, and displacement, and we don't know time, we're going to use this equation. So when we rearrange it for our displacement, we see that we get the difference of the squared velocities divided by 2 times the acceleration. And we can simplify this equation a little bit because the final velocity, or the velocity at time 2, is 0. So let's substitute both of these tools into our total displacement equation. And we have no other rearrangement or simplification that we have to do. So we can move on to the substitution phase. And this is where we're going to plug in all the values that we have. And we try to calculate all at once in one step so that we don't run the risk of rounding off values by calculating them once and then losing some digits in our calculator. When I plug this in, I get a value of 52.7472. And if I look at my values, I have meters per second times seconds. So that's going to give me a meters. And I'm adding that to meters per second that gets squared divided by the units of meters per second squared, which means I'll be left with meters as well. So this is good because I'm looking for a displacement. If we consider significant digits, all of the values we were given have 3 significant digits. You can review the rules from the previous lecture to confirm this yourself, which means our final answer needs to contain only 3 significant digits. So that means it's approximately 52.7 meters. So we have a result, 52.7 meters, but we have to move on to that final statement stage. Remember, we have to answer the question we were asked. We were asked, will the driver be able to stop the vehicle before colliding with the object? And our answer is the vehicle stops in 52.7 meters, which means it will stop before the object that's at 61.0 meters. Remember, it's not good enough to just say 52.7 meters. And it's also not acceptable to just say yes. You have to tell me why your numbers reinforce what you've discovered. And the other thing you can see here is that we've finally used that 61.0 meters. We used it to help us interpret our results. When you complete a test or a quiz question for me, I'm really expecting to see all of this information laid out. Show me that you understand the values given to you in the question. That's our given and sketches. Show me that you can choose the appropriate tools and combine them by giving me your equations that you've selected from the sheet and then rearranging them. I'm not too picky about the number of steps you show me on rearrangements, but you do need to show me how you've combined these equations before you plug all your values in. And to get full marks, you need to show me that you can successfully interpret your results by giving me that final statement. Let's move on to another example. I can throw a water balloon vertically to a height of 7.59 meters. It's roughly the height of my house. If I release the water balloon from my shoulder height at 1.51 meters and it lands on a child whose height is 0.951 meters, what velocity is it traveling at impact and what velocity did it have at launch? So what are we given here? Well, we're given 7.59 meters and 1.15 meters and 0.951 meters. So to understand these values, let's give a sketch. So we're going to set ground level as y equals 0. And then we were told we have launch height. And from there, obviously, we're going to throw an object straight up. So it's going to go up to a point and then it's going to come back down. And then we were told the impact is at the child's height. So we can give these positions in our sketch symbols to represent them. So we can represent the launch height as y1. And we can represent this point in time when it turns around, the max height, as y2, and we'll refer to the child's height as y3. If you wanted, you could even refer to ground level as y0, but we don't really need that here. And what are we asked for here? We're asked for the velocity at impact, so that would be the velocity at position 3, and we're asked for, in a second question, the velocity at launch, so that'd be the velocity at position 1. Well, what else do we know? We should be able to recognize that this is a free fall problem. As soon as I let go of this water balloon, the only thing acting on it is gravity. There would be some air resistance, but I'm not throwing hard enough for air resistance to matter here. So that means we can assume an acceleration that's equal to the acceleration due to gravity. And because we're using up as the positive direction, we'll label this as negative 9.80 meters per second squared. Is there anything else we know? Well, we've labeled a max height. So that max height also tells us that we know the velocity at position 2. It will be 0 meters per second. And with that information, suddenly we realize we have acceleration and velocity and displacement, and we're looking for another velocity. So we're going to use that squared velocity equation again. Let's look at the calculation for impact velocity. So impact velocity means that we're looking at the velocity final, which will be velocity 3 squared, and that's equal to velocity initial, and we're going to set velocity initial here at max height, because that's the only velocity we know right now. And the rest of the equation is that we'll have 2 acceleration, which is constant as g, and our displacement. So this will be our displacement from y2 to y3. We do have to rearrange this equation. This equation is set up to solve for the square of velocity 3. So you need to take the square root of both sides. So that means we're going to take the square root of 2. Our velocity 2 is 0, so it disappears. So that's why we're listing 2 first. Multiplied by negative 9.80 meters per second squared. That's our acceleration due to gravity. And then we have to calculate that displacement. So we're starting at y2, ending at y3, which means we have 0.951 meters subtract 7.159 meters. Now this is all underneath a square root, so you need to be careful and make sure you enter it in your calculator properly. And you should be familiar enough with math to recognize that we can't take the square root of a negative value, so we have to be careful and consider what's going to happen here. Our acceleration is negative, and our displacement will also be negative, as 7.59 is much greater than 0.951. So we'll have a positive value underneath this radical. So when we take the square root, our possible answers is that we could have plus or minus 11.40720.825 meters per second. Remember, a square root is telling us what value multiplied against itself would give us this result. And in that case, both the positive and negative values could answer the question. For us, we know that we're considering the velocity at position 3 when the ball's on the way down, not when the ball was on the way up. One, it doesn't actually hit that point on the way up. So we're going to take the velocity to correct significant digits as approximately negative 11.4 meters per second. So the velocity at impact is 11.4 meters per second down. And that statement answers our question. This was a straightforward question. But the question did have two parts. So let's look at the launch velocity. If I was launching the water balloon from the height of the child, this would be a trivial question. It would be the same magnitude but opposite direction. But I launch it from slightly above the child's height, so I have to do these equations again. So again, let's look at a time interval. I want velocity at launch height. I know velocity at max height. I know acceleration, and I can calculate displacement. So we're going to use the similar equation, but we have to rearrange it slightly differently. So here we'll get our velocity at launch will be equal to the square of the velocity at max height, which is going to disappear, subtract 2 times acceleration times our displacement from launch to max, which means we'll take a displacement of 7.59, our max height that we finish at, and subtract the 1.51 launch height. When we consider our negative values, we see we have -2 from the subtracting and negative in the acceleration. So again, we'll end up with a positive value under the radical. And when we complete the calculation, the calculator spits out 10.91640.967. And we have to look at our units to get meters per second. And we also have to acknowledge that this could be both positive and negative. In our case, we're looking at the launch side, so this will have a positive velocity. But there is an instant when the water balloon is traveling back down where it passes my shoulders with a negative velocity before it hits my neighbor's kid in the head. So we round appropriately to get an approximate launch velocity of 10.9 meters per second up. Interesting part here is clearly I would have just been better off throwing the water balloon directly at the child because it accelerated a little bit by having more time to fall than it did to climb. Units play a very pivotal part in all of our problem solving and our understanding of motion. And when we rearrange kinematic equations, and even when we evaluate kinematic equations, you need to be able to do quick mental checks that we refer to as dimensional analysis. We're looking at the dimensions or the units of the problem. Your calculator's great at calculator things, almost too good at times. You have to be good at interpretation things, and that means you have to determine what the units are from the calculation you've completed. So let's look at an example. So if I told you that you covered 13 meters at a speed of 5 meters per second, and I asked you how long you were traveling, you could look at this and say, okay, I'm given a displacement, and I'm given a velocity, and I'm asked for time. So I could start from my definition of velocity being equal to displacement over time, and then I have to rearrange. Hopefully you're comfortable getting the correct rearrangement. That time would multiply up and velocity would divide back down, giving us that time is equal to displacement divided by velocity, which gives us units of meters divided by meters per second. Now remember, whenever you're multiplying and dividing fractions, you have to be careful. When you divide fractions, we actually multiply by the flipped over version of the bottom fraction. So this is the same as saying meters over an imaginary 1 multiplied by seconds per meter. And when we simplify this, we see that we end up with units of seconds, which is really good because that's how we measure time. Now, what if we got the algebra wrong? And there's two ways we could have got the algebra wrong here. We could have decided that, oh, we just have to multiply time up and across and then multiply velocity back, and that gives us time is equal to velocity multiplied by displacement. And if we do that, we're not going to be happy, but let's look at another way we could have gone wrong. We could have accidentally flipped velocity and displacement. You may be rolling your eyes looking at these, but I assure you some very smart students, when they're rushed on quizzes and tests, make these silly mistakes. So it's important to make sure you're giving yourself time to do the mental check. So what would the mental checks look like here? In the first incorrect rearrangement, this would give us units of meters per second multiplied by meters, which simplifies to units of meters squared per second. And that's not helpful because that's not how we calculate time. So if our units are wrong, our numbers are wrong too. And the number itself may not be immediately evident that it's an unacceptable answer, but the units should be more evident to you. Let's look at the second example. It's a little more complicated. So now we have meters per second divided by meters. Again, we have to take the reciprocal of the second fraction, which means we're going to have meters per second multiplied by 1 over meters. When we cancel out the meter on the top and the bottom, we're left with the units of per second. Well, those are units we'll discuss later in the course. These are not the units that we use to measure time. So again, we would have seen that we've got an incorrect rearrangement. We'd have to go back through our problem and try and find out where the error occurred. Even if you're not doing rearrangement, dimensional analysis is important so that you can ensure you've substituted the correct values into the correct part in the equation. And if you're not sure what you've calculated, it also helps you look at all the values you've combined to see if you end in the correct units that you were expecting. We've covered a lot in this lecture. We were really looking at our general physics concepts of motions, which means we introduced the key quantities of position, velocity, and acceleration. And we also defined the kinematic equations that we're going to use to solve problems. Now, I don't expect you to memorize equations. You are getting a formula sheet that has many equations on it. Your job is to understand those equations and to know how to apply them. We also refined their problem-solving approach, so we looked in more detail at that GRASS method and how it should appear when we're solving problems with it. And we looked at this in the contents of considering how do we choose equations. Remember, you're looking for one equation with one unknown, which means you're trying to pick the equation that has the thing you're looking for, and only other variables are the ones that you are given in the problem. And the last thing we considered after solving examples was we may have realized the reason why I'm not allowed to babysit my neighbor's kids anymore. After all, that water balloon was traveling about 41 kilometers per hour.